Every single second on the modern battlefield generates a chaotic, asynchronous, and overwhelming flood of raw sensor data. The U.S. Department of Defense has officially designated the Maven Smart System as the primary operating system for real-time kinetic operations. To feed that system, contractors like Palmer Luckey's Endural deploy advanced hardware that captures continuous streams of environmental intelligence. That fragmented hardware data is then fed into an overarching software platform provided by Alex Karp's Palantir. Success in this environment depends on the model's ability to parse raw, unorganized noise into actionable context. A neural network requires structured data to function. Without it, even the most advanced model fails to navigate the entropy of a live engagement. To understand how this works, we can reverse engineer the architecture of an autonomous targeting platform from first principles, strictly using off-the-shelf, open-source data engineering tools. The creation of lethal autonomous platforms has moved from the realm of classified weapons development into the domain of high-scale data engineering. Analytically, looking at this architectural canvas, we have to start at layer 1, ingestion. The system is bombarded by distinct, overlapping data formats simultaneously, from satellite GPS telemetry to drone video streams to text-based special ops communications. To manage this high-velocity, asynchronous event streaming, we deploy an infrastructure tool like Apache Kafka. Kafka prevents system failure by instantly publishing these varied inputs into isolated, highly organized parallel channels known as topics. But organized raw data is completely useless to downstream logic. A perfectly streamed sequence of video pixels means nothing to a targeting algorithm. At layer 2, we introduce Apache Spark, which subscribes directly to those Kafka video topics to process the streams. Spark operates in tandem with computer vision libraries like OpenCV to actively scan every incoming raw video frame. OpenCV automatically segments the image, detects specific objects within the visual noise, and generates highly structured event logs. In milliseconds, gigabytes of raw pixel data are compressed into a tiny, structured text payload containing an object type, a GPS coordinate, and a confidence score. The transformation layer distills the physical reality of a battlefield into standardized, machine-readable text. We now have thousands of structured data points, but the system still lacks a way to map the physical relationships and spatial movements between them. This grid represents a standard relational database using SQL, how traditional architecture stores organized information. In warfare, relational tables break down. When you attempt complex, real-time table joins to track dynamic entities moving across a 3D space, the queries overload the rigid structure. Modern kinetic operations require an architectural pivot to a graph database. Palantir refers to this structural concept as the ontology, a shared digital clone that maps fragmented information into a unified physical reality. This 3D network diagram shows the mechanics of an open-source graph database like Neo4j. Here, physical entities, people, vehicles, and munitions are stored as discrete, independent nodes. As those entities move, their proximities and affiliations are rendered dynamically as edges, drawing real-time connections across the layout. Without a physics-based graph database to model these precise relationships, AI agents lack the spatial context to differentiate an enemy asset from a civilian zone. Before an AI can act on this digital twin, the platform must establish strict, non-negotiable rules of engagement. To govern the system, we implement Open Policy Agent, or OPA. OPA functions as policy as code, programmatically enforcing operational rules across the entire software stack before any action is authorized. With governance in place, we reach the final step, the agentic layer, where large language models are deployed. Defense systems rely on the complex reasoning capabilities provided by top-tier LLM developers like Sam Altman's OpenAI. But an LLM cannot natively read a complex graph database to extract that reasoning. We bridge that gap using the Model Context Protocol. This protocol translates the LLM's natural language reasoning into precise graph queries. It allows the AI to pull immediate context from the ontology and authorize a strike payload based on validated data. By providing a secure bridge to the graph, MCP allows the model to act as a reasoning engine for the system, translating raw database relationships into prioritized tactical recommendations. Zooming out, this assembled diagram reveals the complete operational architecture. Chaotic ingestion is sorted by streaming, standardized by real-time transformation, mapped by a graph database, governed by strict code, and finally queried by an AI agent to prioritize a target. This specific sequence represents the exact logic loop powering live deployments like Project Maven. Historically, autonomous military software was assumed to require proprietary technology built on trillion-dollar defense budgets. But every tool we use to design this system is standard, off-the-shelf open-source software. The exact architecture capable of turning individuals into data points and data points into targets relies on the same technology stack, currently running global enterprise shipping logistics and back-end web applications.